So if we had a wire going like this in a loop, we could actually use the right-hand rule to determine the magnetic field will be pointing in that direction. But we're actually going to use this little integral to derive that and see how we actually get that. So first thing we're going to notice is this little cross product here. So get the dl cross with r. If we were to try to evaluate that, we'd see that it would be dl and then just a regular old r and then sine of theta. And so we would need to take a look at the sine of theta. It's going to be the angle between these two vectors, r and dl. So dl would be pointing something in like that direction, which would just be going along the current, and the r would be pointing in like literally that direction. Kind of small there, but if we were to go perfectly straight there and then sort of curve and go perfectly straight there, we would see that's a 90-degree angle. And it's hard to see that, but it's definitely 90 degrees in there. So this weird little angle over there, that's 90 degrees. So that's the sine of 90 right here, which is just 1. So that can kind of go away. And then r is just 1, so that'll go away. And so we're just left with dl. All right, that's nice. So we'll also pull this r squared out of the integral because it's a constant. So technically, we're just going to be getting something like this. I over 4 pi r squared, and then just the integral of dl. Now, the L is supposed to be this circle, so, we kind of know that the dl is going to be like r d theta, and and this is supposed to be a capital R here, a lowercase r there, because we got 2 different r's, but this is just going to be, r and then times 2 pi, because it's a circle. So that's basically what the whole answer to the integral is. It's pretty easy. So mu naught I, and then we have the r, and then here's a 2 pi, and then it's going to be divided by 4 pi r squared. We're not really quite done yet, because if we were to remember the cross product over here, dl cross r, notice where my thumb ends up pointing. It ends up pointing in this direction. So now we kind of want to do that like on the other side and notice that there's actually a symmetry happening. So you would get this kind of stuff in like a little loop everywhere. So like these portions are going to cancel out, and the only thing you're going to get is the sideways portion right here. So that's how we actually figure out that it is only in that one direction there, because all the other ones are just going to cancel out. So we're left with trying to figure out this angle here and asking yourself, I guess I'll make it a phi here. And we'll see if we want that component of the phi, that would be the cosine, because it's in the x direction, right? If we kind of have, this is the hypotenuse, this is the adjacent angle, so we're going to need to know the cosine of phi. So the cosine of phi is a little bit harder to figure out which angle this is, but it seems like it might be this angle, but it's not. It's not that angle. Even though it might seem like it, it's actually not. Okay, that's why it's kind of important to maybe even draw multiple positions for this spot that we're seeing. So then you'll actually see that as you come closer here, these things will start to kind of become more like that. And then as you go further out, if you were going all the way out here, for example, you'd start to notice that these arrows start to point really high up like this. And then you get like a really wide angle here and like a really, really small angle here. So those two things are not equal. That is not the same angle as that. So that's why we have to be a little careful, because it's not this angle. Even though it looks like it, if you draw it in the wrong spot, you might get confused and think that that's the angle that you're looking at. It's actually this angle, which the way to find that angle is actually this one over here. Is this freaking angle. This one. So Yeah, it's kind of weird. Actually, I'll draw it in this one. So it's the orange angle here that we care about. So let's try to figure out what that is. Cosine of that one is going to be the adjacent, which is r, divided by the r. So I know it's a little bit complicated, but that's really important. Now we're going to use the cosine of phi as r over r. We can plug that over here because we're going to need to know the cosine of phi here. They're just taking only that component of this. We could replace that with the r over r, and we'll basically get, let's delete some of those things. Let's make this a 2 on the bottom, and then we're basically left with MOI r squared divided by 2r to the third. Now let's try to figure out what this r is. R is just going to equal, it's like z squared plus r squared. Z squared plus r squared, and then a little square root thing. If we had r to the third, then we would just go like this. And then we'd see that this is z squared plus r squared, which is 3 over 2. And that's what we can finally plug in for the answer here. B equals mu naught I r squared divided by 2 times the z squared plus r squared, 3 over 2. And if you have 2 of these loops, one here and one there, and the current is both in the same direction, it turns out that you're just going to have to get 2 of them. So here's another example. There's a loop right there. This has to do with one of the problems we're working on. If you get another magnetic field pointing that way, it's actually also going to be on the other side too. Let's not forget that. So there's going to be one on this side as well. And so when you get 2 of them stuck together, you're actually just going to add those 2 together. So I'm going to multiply this by 2, getting rid of that. And so now you know if there's something right in the middle. And depending on the number of coils, if there is a necessary number of coils to put in there, you're going to be going like the MOIR squared divided by z squared plus r squared, 3 over 2. And then there should be an n for the number of coils. Now I believe that n, the number of coils, is referring to how many coils we have like around here. If I keep going like this in a circle and I keep making this turn around a million times, like how many coils do we get in there? And you might have to add that n into the equation.